Okay guys, here we go with 10 questions on centripetal forces and acceleration. We'll start with this one. This is all about the centripetal forces acting on a car as it follows a horizontal circular path. I've stolen an image here from drivingfast.net, so thank you very much for that. Here we've got to remember that remember our circular motion, and firstly the thing to think about is where is the center of the circle. I would encourage you always, whenever you're thinking about a problem like this, to think of where is the center. Now clearly he's following a path. This is this red one here, and there is a curve curving off to the right here, so that means my center is somewhere off in the middle here. Okay, now remember our centripetal force, if we want to continue having our circular motion, it must act towards the center of the circle. And so therefore, we can actually rule out two of our answers, B and C, because they are telling us that the force must be away from the center of the circle. The question is, where does this force come from? Well, remember the car engine will produce a thrust, and the thrust will actually be somewhere along this, pushing us along this green line, because it allows our wheels to move either faster or slower or at a constant speed, and therefore continues our motion. So if you like, the force produced by the thrust may be considered to be along, for this purpose, is maybe along that green line. However, the friction between the tires and the road is the one that's stopping our car from slipping and is therefore acting towards the center of the circle, which is the reason why our answer here is there, is the friction between the tires and the road, it is towards the center of the circle. Now in the second question, we're dealing with exactly the same question. However, this time, we're told it's at uniform speed. Okay, it's a cyclist, but we can just represent that as a car, that's fine. Again, we've got a centripetal force, i.e. a friction force, which is acting towards the center of the motion. Now, clearly, if we want circular motion to happen, this force needs to be non-zero. And so therefore, again, we can rule out A and C, and we're left with just these two options. So the question is this horizontal force along the direction of motion, and then has to be considered at this point. Let's think about the car at this point in the motion. The horizontal force along the center of the motion, so along the direction of motion, so for example, this red arrow here could also be pointing in the other direction. Well, we've got a uniform speed. If there's any force, either pulling the car back or pushing it forward, then my speed is going to increase or decrease. And so therefore, it wouldn't be uniform. Therefore, this force, this red arrow, must have a zero value. In other words, it must be non-existent. There is no friction, or no, we should really say, no net horizontal force. There may be friction, however, that is balanced out by the thrust of the engine. This is a good question because it tests your reading of an understanding of where centripetal forces come from. Remember, centripetal force itself is not a type of force. It is just a name that we give to the resultant force acting on an object doing circular motion. Now in this case, there are only two forces acting on the plane which are adding together to produce our centripetal force. So we need to choose a diagram where there's only two forces. So that means we're looking at either B or D. Okay, the centripetal force, the net force, is the sum of the weight, and in this case, the lift force. Now, lift force is just like the normal reaction force. It is normal to the plane itself. Okay, so actually the answer here is D, and we'll see why. Well, we know that we've got centripetal motion, we've got centripetal force, and that centripetal force must act towards the center of the circle. Okay, so the center of the circle is somewhere over here. We need to produce a force, in other words, that is to the left. If we have our weight acting down and our lift force acting up, we use our tip to tail method. We've got weight plus lift adding together to produce this red force, which is my centripetal force. Okay, so in other words, the answer here is D. The key point here being that centripetal force itself is not a force, it is just the name we give to the resultant of one or more vectors which are adding together to produce circular motion. Communication satellite is moving at constant speed in circular orbit. At any given time, the resultant force, let's go through the different answers here. The resultant force on the satellite is 0. Well, that can't be true because we've got circular motion. If you've got circular motion, a circular orbit, we must have a centripetal force. It must be non-zero. The answer here is B, because the gravitational force on the satellite is what provides the centripetal force. And in this case, we just equalize them. If we know the gravitational force, we know the centripetal force. Let's have a look at the parts C and D just to make sure that we're okay here. C is a bit of a confusing one, and again, this is where we have to remind ourselves of what actually the centripetal force is. The centripetal force is the vector sum of all of the forces acting on the satellite. Okay, and so therefore, it's kind of wrong physics to add the centripetal force to the gravitational force because the centripetal force is provided by the gravitational force. In other words, it is equal to that. The last one, equal to the force exerted by the satellite's rockets. This is an interesting one, and again, we've got to think about our direction of motion. The force produced by the satellite's rockets will be presumably to maintain its linear speed, its tangential speed, and that will be to oppose air resistance. Now that is at 90 degrees to my gravitational force, and so therefore it does nothing to the centripetal force. It doesn't contribute to that. All right, bit of maths here. Okay, here we'll look at our forces. Okay, we've got horizontal circular motion. We need a centripetal force, therefore, which is pushing towards the center, and i.e. pushing left on the little bob there. Okay, so let's think about resolving our forces. We look at the vertical forces first. We know that we've got weight hanging down. Okay, we've got mass pulling, mass and gravity, therefore pulling down, and we are moving in a horizontal circle. Therefore, we assume the vertical force is to be balanced. The vertical force provided by my tension in my string. If there's a tension here, T, we take cosine of that angle, and therefore we get the vertical component. T cos theta is equal to m times g. That's the weight. The centripetal force must be provided by the horizontal component of my tension. Well, if the vertical component is cos, then the horizontal component is sine. And we can express this in multiple ways. However, because we've got an omega in all the answers here, I'm going to go for this. This is my centripetal force equation, m omega squared r. Now, here's a nice trick for you. What you can do is take the second equation and divide it by the first equation. If these equations are all equal to on left and right respectively, then we should be able to divide each side, and we'll get something out of it then. If I take t sine theta, the left-hand side, and divide it by t cos theta, that's the left-hand side of my first equation, then I've got m omega squared r divided by mg. Again, right-hand side of each respective equation here. You notice here my m's are going to cancel, and so are my t's, and I'm left with sine theta over cos theta. Now there's an identity, which is that sine theta divided by cos theta is equal to tan theta. In other words, we've got our tan theta is equal to omega squared r over g. This is a very commonly used trigonometrical trick, and it's well worth reminding yourself of this one. Okay, this is a nasty question. Okay, we're looking at a motorcyclist on a curved bank. Okay, and we want to think about the centripetal force on this thing, and then we'll go from there. We're really being asked to say what combination of these factors will allow us to go faster. Okay, let's go through this. Now, the centripetal force is given by this equation here. mv squared over r is equal to n sine theta plus mu n cos theta. Mu here is coefficient of friction, and theta is the angle. Where does this come from? Well, we've got a normal force here, n, and therefore a component acting towards the center of the circle. We've also got the friction force, and it has a component, and I've put this just on the bottom here as well. The centripetal force is going to be the sum of these two forces. We can chuck in our angles here, okay, and we end up with our we end up seeing that where our angles fit in to our triangles here. The component in the red is just given by the value of n multiplied by sine theta. We're looking at the opposite to the angle, so that's n sine theta. Our blue component is the friction force, mu n, multiplied by cosine of theta, okay, because again, we're looking at the horizontal here. That's where this equation comes from. It's the sum of the blue and the red dashed lines, therefore, here, okay? And you can see here that if I increase theta, I increase the value of the centripetal force that I can provide. The sine of theta, theta is going up, and therefore my V can increase. Similarly, if I increase mu, again, my centripetal force is going to increase, and so therefore the value of V can also increase. Now, there is a small, so this is the answer here, A. There is a small caveat here. We are assuming that your increase in mu is greater than the decrease in cos of theta due to the increase. Because remember, as theta goes up, cos goes down. I think this hasn't been quite assumed in the question. Just be careful with that. I kind of overthought this one for a little bit, and then I realized actually there's a little bit of physics there that needs to be explained. Don't worry too much at IB level. Okay, here we go with a mass attached to a string in a gravitational field. That's important. We've got weight. We want to think about the tension in the string and the kinetic energy of the mass. Let's think about this here. Firstly, when we are rotating, we do in this vertical plane, we've got to think about our energy conservation. Okay, at the bottom, we have got lower potential energy than in the middle or at the top indeed. If we've got low potential energy, we're thinking about energy conservation. Low potential energy means high kinetic energy. And so in other words, the kinetic energy at Q must be greater than the kinetic energy at P. Therefore, we're looking at either A and B. Let's think now about the tension. Well, I like to think about the top and the bottom actually. At the top, we've got centripetal acceleration, okay? That is being provided by both the weight and the tension. In other words, the weight and the tension are in the same direction. Now, the result of this is that the tension is very low at the top. As we come round to the bottom, the tension and the weight are in opposite directions, okay? So in order to provide the centripetal force, our tension at Q has to do two things. One has to balance the weight, and it also has to then produce a centripetal force. And in other words, what that means is that the tension in the string is greater in Q, is at its greatest in Q, and it's also got the highest kinetic energy. You're going to see a derivation of this in a second in the following questions. Okay, again, this is our kind of same idea here. Instead of going in a vertical circle, we're doing vertical pendulum. However, really the physics is the same. At this bottom point, we're doing circular motion. We've got a weight acting down and tension going up. And so therefore, the tension take away the weight is the resultant force. And the resultant force for centripetal acceleration is mv squared over r. Okay, we can then rearrange this to show that T is equal to mv squared over r plus w. In other words, the tension is greater than the weight of the mass because we're having to balance the weight and then add the centripetal force on top of that. Last two related ones here. Again, we're going in a vertical circle. Okay, we're looking at our answers here in terms of our tension and weight again. Thinking at the bottom of the circle, again, the tension and the weight are in opposite directions. So tension take away weight is our resultant force, and our resultant force is the centripetal force. I've used m omega squared r here because that's in the question. M omega squared r is equal to the difference between the tension and the weight. Okay, well, we know that weight is mg, and I can therefore rearrange this so that I've got T is equal to m omega squared r plus mg. In other words, T is equal to m omega squared r plus g, where we've taken out a common factor there of m. Last one, and again,